Hey, hello everyone. My name is Mildred and this is Python for Data Science. Today we are going to go through all of the fundamentals of data science. We are going to look through all we have done so far and we're going to simulate a data set. We'll try to simulate healthcare data set and we will use that for today's lesson. And then hopefully if we can cover everything, we'll try to use a different type of data set for next week where we'll focus majorly on modules week 7 to 10 to look at the different things that we have learned so far. Now, when we talk about data science, we want to actually understand what data is and why we actually do data analysis. First of all, if we want to have meaningful interpretation, we need to have data, not just data, but usable and meaningful data. And this useful and meaningful data has to be collected from somewhere. We have different data sources online where they have open source shared data. We use different API methods or HTTP requests to pull information from those sites without having to create a database to store those information if we need it. And we use that for interoperability where we can link several systems together. So we started in week 1 by looking at the different HTTP methods in Python and we look at what a JSON file is. We moved to week 2 where we looked at the series and pandas data frame. We also looked at all the different operations that we can do, how to import and export data in the different formats, how to index, slice and filter data. We looked at the label position. We looked at Boolean filtering. We also went forward to look at NumPy. We look at how we aggregate and group and do group operations. We look at how to transform when we group, and we look at how to do multi-index and group by. And we hope that we will be able to revise this before this course finishes, because we want you to leave this course being able to talk about data and talk about all of the possibilities and the things that you can achieve when you have data. In week 3, when we introduce NumPy, we look at NumPy and we look at what broadcasting is, which are things that we will need as we analyze complex data. We look at how to clean data and prepare data for exploratory data analysis. We see how to do data type conversion when we clean, how to detect, duplicate and to remove, outlier detection, and the different things that we can do when we meet all of these different kind of messiness in data. We also looked at the different ways that we can handle missing data and handle outliers. We looked at the different ways that we can inspect the data, and we went on to use visualization and look at the different visualizations that we have. We have used different tools from Matplotlib to SciPy. We have used Pandas, NumPy. We have also used other like scikit-learn when we want to load the iris data set. As an example, we try to use Plotly, Seaborn, and all those for interactivity and different types of plots or bar and charts. Now, from week 7, we began to look at exploratory data analysis in a different context. Can you all hear me?
Yes, yeah.
Okay. So we began to look at exploratory data analysis in a totally different context, and we looked at it using everything that I have said so far and looking at the workflow of how we first fetch the data or identify the data source. Then we work with Pandas series or data frame. We'll look if we want to index, slice, filter, perform aggregation or grouping, want to clean or transform, and we want to generate descriptive statistics. We want to detect outlier, visualize with box plots, parse data and time field if we have them, integrate SQL if we need to save data in a database for retrieval. And then we looked at all of those different visualizations and what each of them mean. So today now, we are going to run through exploratory data analysis, and then we're going to use a case study and ask ourselves what is it that we're trying to do, and then see how we can tie this up into visual storytelling. Now, exploratory data analysis is just that process that we use to investigate data sets. And anytime you have data, you need to, first of all, look at the raw data. You want to investigate that data to understand the structure and the pattern. You want to see if there are any anomalies in the data or any errors. You want to create your own assumptions. Before you come, you already have assumptions, so you want to test your assumptions, you want to discover relationships, you want to generate hypotheses and the likes. So it's like, first of all, when you have data, the first thing you do is to ask questions from that data before you model it. So you just want to get to know your data before you can say, I trust this data, it is usable for the kind of questions that we want to answer. And then we have different types of analysis. When we do univariate analysis to examine a single variable and understand the behavior and characteristics of that single variable. And then we do bivariate analysis, where we investigate the relationship between two variables and we'll determine how those variables interact, whether they are correlated, and if the dependency exists between them. And mostly when we do bivariate analysis, we use scatter plots to visualize relationship, we use correlation coefficient, we use crosstabs, we use line graphs to see changes, and covariance to determine how the variables vary together. When we talk about univariate analysis, we use histograms, box plots, bar charts, and the likes. Then we have multivariate analysis, where we examine relationship involving 3 or more variables, and we use scatter matrix. We can use principal component analysis, which we'll do in machine learning, not in this course. And we do spatial analysis, where we use map to interpret geographic patterns. That's one of the use cases. And then time series analysis, when we want to study trends and patterns. And so we have different steps that we perform exploratory data analysis, from cleaning to manipulation to basic visualization to enhanced visual plots, and then we can have interactive plots. And so the first thing, we want to understand the problem. Now, I have this seed data that I have generated here, and what we want to do is to simulate healthcare data. So we are not using real healthcare data, but we're using a simulated one. And this data that we're simulating, we want to have a data set that we can use to explore the data and begin to go into all those advanced things, from visualization to hypothesis and testing. Now, the clinical context for this is we're using the United States, and we know that hospital readmission within 30 days of discharge is one of the most expensive, preventable problem in healthcare. So the problem is, like, people are admitted, they are discharged within 30 days, they are readmitted again. And in the United States alone, unplanned readmissions cost the Medicare insurance over $26 billion annually. So the Centers for Medicare and Medicaid Services penalizes hospitals that have high readmission rates. And so now they use data-driven models that identify all of the patients that are at risk before the discharge, and that helps them to reduce the hospital readmission rate. Now, this data set we use now simulates a real-world hospital cohort study, and what we want to do is to analyze clinical demographic and all the operational variables that are there, and identify which factors that most strongly associate with 30-day admission or 30 days readmission. So when you get all of the historical patient record, which we are simulating here, and we want to look at just some basic records and then some operational record. What we are measuring now is the patient demographic, where we have the patient ID, age, gender, and the ward where the person was admitted. So we just want to use cardiology, general oncology, orthopedics. And then we have the clinical measurements on admission, like the length of stay, the number of previous admissions in the last year, the medications that are prescribed, the comorbidity score, so any combined illness that they have, the blood pressure, the systolic blood pressure, the blood glucose, and we use the BMI also. Then the operational and behavioral measurements we are going to use is the discharge type, the follow-up attended, and then the insurance type. Now, the outcome variable, that is the 30-day readmission. We want to see if readmission probability increases with the comorbidity or prior admissions or self-discharge or missed follow-up, and we want to get a realistic clinical signal. So the readmission probability that we have here, we try to generate this probability like this. So we have 0.10, and one thing about probability is, which is week 8, is the total of all will be equal to 1, right, for probability. And so we simulated this to get probability distribution of this. So we have 0.9 and then 0.05. And we just generate this to just get probability score here. Okay. And then we have the missing values. We just want to inject just for us to practice. Okay. So this is our simulated data set, and I look at the shape 415 here. So we're working with this healthcare data, and every row of this data will represent one patient that is admitted to the hospital. We have all of these clinical measurements for each patient in that row, and we want to ask the question, did this patient return to the hospital within 30 days of discharge? That's the first question we are trying to answer. So when you are doing data science or data analysis, what is the question you are trying to answer? Is the first thing you ask. So can anybody tell me what is another question you can generate from this data? Anyone?
Sorry.
Yeah, so I was asking, can you think of looking at this data, if there's any other question that comes to mind that you can use this data to answer a research question? So I can even use this data to, okay, sorry, go on.
No, I said I'm not able to think of that question.
Okay, so right now we have a question we want to answer, which is what makes people to return back to the hospital within 30 days of admission. So we want to say, the question is, did this patient return to the hospital within 30 days of discharge or readmission? That's the question. And we can even look at this data and say, we can ask another question to say, if people who stay longer on admission, people that stay longer on admission, the general well-being, is it better? Do they stay healthier for longer than people who are discharged early? So apart from the 30-day mark we are trying to investigate, you can just look at the overall thing and say, what is the rate of admission of each patient and what makes that admission rate? Are people who are admitted frequently diabetic? Are people who are admitted frequently with high BMI? So there are several research questions you can have when you have data, and the kind of story you can tell with this data will now begin to change the direction of policies and allocation of funds and all of that. So by nature, healthcare data is messy. You can't see a healthcare data that is this clean. It is very messy by nature. And so when you do lab tests, results comes in at different times. Patients can miss follow-ups, so you have missing values. The values can get recorded incorrectly, different units of measurement, different nurses do different things. So this data that we simulated now, we do that to reflect this, and so we want to pay attention now to how we handle all of these professionals, because you rarely ever get clean data. So as a data scientist, the first thing you want to do is to inspect your data and understand, first of all, why you have different columns, what is going to be. Do you want to drop columns of data? Do you want to check? So the patient ID we have here is a 4-digit integer that we use for patient ID. As we can see, we have age, which is an integer in an integer years. We have sample from age 18 to age 90, right?
You also likely have patients that won't survive, that may die in the process of admission.
Yes. So there are many outcomes or things that you can do with the data. But when we talk about patients that will die right now, we don't have any column that talk about whether a person is dead or alive. They put home care facility self-discharge. So discharge type, that's where we come to data re-engineering, where we now begin to say this person was admitted, but there was never a discharge. So we want to check death record, we want to check the final record if the person was marked as dead, and then we'll now re-engineer a column where we'll say if the column is missing, if the discharge type is missing, mark it as dead. Do you want to go that way? Or we want to check and see if they just forgot to enter it and the person was really discharged. And that's how we clean and re-engineer data. So we can now say we have a general rule to say we want to know how many people left the hospital alive and cause of death. And so now we can look at discharge type and re-engineer and give a command to say any missing value in the discharge type should be filled with dead or something. Did not leave the hospital. So you see, you re-engineer data and ask a different research question. So that's very good. So we have categorical data. When we talk about categorical data, is grouping people into groups like gender, male and female, any other gender. So we have equal split here. We made this equal split, male and female, approximately equal anyway. And then we have the word. It's also categorical here. I choose one word. So we just represent the clinical department. The length of stay we have here is an integer and is in days. We have the number of medication prescribed by discharge. We want the number of medication to be, we'll put maybe 1 to 15 here. Number of medications, we want more 1 to 15. So 16 is non-inclusive, the last, so we'll do 1 to 15. And then we want to put number of previous admissions and the past 12 months, the count of previous admission will just use the poison distributed, which will be 1.5, right? So by default, we want the number of previous admission will be the mean is 1.5, and then we have number. Then we want to have the comorbidity score. So when we use Chaucin Comorbidity Index, you might know this if you're an epidemiologist, or you don't really need to know it. You always have a manual that tells you exactly what all of these different things mean. So when we say you have a comorbidity index 0 to 5 or higher, so we have the Chaucin the Chaucin's comorbidity index to be 0 to 5, and the higher one, once it's have more chronic conditions like diabetes, heart failure. Okay, so that's the score we use 0 to 5. And then we have the systolic blood pressure. We use the normal is between 90 to 120, and then the mean will be approximately 130. Then that's what we are doing there. So when we look at this, we understand all of this. So now we have talked about the data, and I might send this seed data to you so that you can use that to practice after the class. So the research questions that we want to keep in mind throughout is: which clinical factor, is it comorbidity, is it blood sugar, or systolic, that are most strongly associated with 30-day readmission? We also want to ask that do these patients that missed, or do the patient that missed follow-up, do they have higher readmission rates? Or does the length of stay in hospital differ between the different wards? We want to ask, like, is readmission rate associated with the insurance type or the method of discharge? And then we want to ask if there's any significant difference in all of these clinical measurements between readmitted and non-readmitted patients. So you see these 5 questions we have. It will help us to explore this data and answer all the statistics questions we'll have by week 9 and 10. So the first thing is to load the data, which we have done. That's for exploratory data analysis. We load the data. In clinical data science, right, a wrong assumption will have real consequence. So you want to make sure you know what you are doing, mathematical, scientific, and also you are making sure this data makes sense. You're not having outliers that will throw off the balance. You need to be able to trust the data you're using, and you need to be able to tell a story with your final outcome. So before we calculate a single statistics, we want to audit this data. And in a hospital setting, a missing value is not just any technical inconvenience. It might mean a test was not ordered, or a patient refused the test, or a result was never recorded. So the reason for the missingness is one thing you need to bear in mind, because different domains have different reasons. And so you don't use one rule for exploratory data analysis. You now use your scientific sense, your data analysis skills to know that in this domain. So exploratory data analysis is heavily domain specific, in the sense that when you are exploring, you have to keep the domain in mind, and you have to have a lot of domain knowledge. We have the dimension already here, where we have the shape to be 415, right? And we previewed the first 5 records here. So the column types that we have, we can print df.info to see the column types. Let me remove this and say df.info. So we have column types we have. So you can do df.info and you see the column types here. See the data types, and you see the patient ID don't have any null value. Everything here says non-null, non-null, null. We have not put in like null values here. So we have column types and non-null counts. All right. So the number of columns that are not null, here we have patient ID we don't have anything null because we have 400 rows. But when we come to comorbidity, after comorbidity cause systolic blood pressure, we have 384 that is not null, which means we have some null values here. It means we have some null values here. We have some null values here. So when you see 400 is not null. So now you know that there are columns that have null values: systolic blood pressure, the blood glucose, and BMI. And if these are not recorded, what do you need to get the BMI? Is it the weight? So if we have BMI not filled in, and the weight is filled in, and the height is filled in, we can do data re-engineering to get BMI automatically. So that's what you do when you do data re-engineering, to produce a new column based on the other columns that did not exist initially. So now we don't have those columns of information. So what do we do with these missing values? That's the next thing we think about. You don't think about it as a general rule that I want to use median or I want to use mean, but you think about it in relation to the domain where of analysis that you are doing. So in healthcare data science, we have missing completely at random and the different types of missing data we have. And so the missingness is random and it's unrelated to any variable. So you cannot say this one is missing because the person is dead. It's just not related to anything. All right. So we have those missingness that is unrelated, and then we have the missing completely at random first. Then we have missing at random, which is related to other observed variables. Like glucose is only measured in patients that are flagged as diabetic on admission. So like that's just missing at random. And then we have missing not at random. So I'll write it here. What we have in healthcare data, we have, you will see MCAR like this, which is missing completely at random. And the meaning of this is unrelated to any variable. Maybe the lab machine was offline, or the lab did not record at a random hour. And then you have missing at random like this, which is just that the value is missing randomly based on the fact that that test was not needed for that patient or something like that. So if the patient is not diabetic, there's no need to take the blood glucose every day. So you're missing at random. And then we have one we call like this, which is missing not at random. So the value itself is just missing, maybe because patients that have very high blood pressure, for instance, just refuse to measure their blood pressure out of anxiety. Okay, so it's not missing at random, but it's missing and because of something, and it relates to the patient's overall health. So while the missing completely at random is safe to impute with your median and mean, right? Missing at random requires your careful study first, because if it's missing at random, you want to really know if it's really missing at random or they forgot to enter the value. All right. And then if it's missing because of the patient's anxiety and something, then you have to strategize differently what you want to replace the missing values with. So missing completely at random is the one that is safe to use median or mean to replace those ones. Now, when we look at these rows, look at all of this patient information, what particular column does not make any sense to have in this analysis we want to do? Can anybody tell me, looking at the column, what column will you think that we don't need at all? So that's one of the things of exploration data analysis. You take columns you don't need, you just drop them out, and you just focus on columns you need, and then you re-engineer columns that you need but you don't have, but you have enough columns to generate or to create columns out. Like maybe you have the date of birth, you want to compute an age column, or you have the weight and the height, you want to compute a BMI column. So can anyone tell me in all these columns of information, patient ID, age, gender, ward, length of stay, number of previous admission, all of this, which particular column will not make any sense in this analysis that we need to drop and take away?
Maybe the insurance type may not really be necessary now.
No, insurance type is very necessary because one of our research question is readmission rates associated with insurance type or discharge method. So we need insurance type. So I'll tell you one rule of exploratory data analysis. Anything that is an identifier is just arbitrary. It does not make no sense to have a patient ID. These are just arbitrary identifiers. So you want to drop any of those arbitrary identifiers before you even start your analysis. First of all, look at what column will not make sense. I don't need a patient ID for anything. We're not trying to look at what patient. We're trying to look at data itself, and we're trying to look at readmission and want to look at all of the factors that affect. We still need the gender because are there more males and females? What constitutes it? We still need the patient's age. Is it by age? Is there a correlation between age and it? So those are the things. So one of the things we don't need is the patient ID. And so we can drop this patient ID. So we can do, we create a new data frame. Let's call it DF analysis. And we'll say this is equal to DF.drop. So this is how we drop, right? We're going to drop the columns and then we just name just the column and in quotes, and the column name is patient ID, uppercase, camel case, like this. Okay, so we do this and we have this. So let's say DF. You always use head to view the data that you have. You have to make sure that you're on the right track, but you don't leave print statements in your final script. So look at the patient IDs out of it. So now we know that we don't have patient ID anymore. Do you have any question now? Okay. So now the next thing we want to do is to quantify every numeric variable that we have. And in a clinical context, each statistic has meaning, and the meaning is just beyond numbers. You can't. The age is not just a number here in clinical cohort. The systolic blood pressure is not just a number. The blood glucose is not just a number. So because we have, let's say, a mean systolic blood pressure of 130 millimeter mercury will tell us that this is a hypertensive range cohort, right? But a standard deviation of 28 or for blood glucose will tell us that there's high variability. So something like that. So some patients are severely hyperglycemic, and then we'll read. So when a clinician read these numbers, it is not just a number. Okay. So once you are doing this kind of analysis in that domain, you need to be able to think in that domain. And most of the time, you'll be given a manual of indicators and their definition. And so as a data analyst, once you are able to be a data science, you're able to be a software engineer, your mind runs even wilder than you know. And so the limit of your mind is just the power of your imagination. And so any field you get into, you can study it in the context of what you need to do and understand it. And you need to understand it for you to move. Have meetings with stakeholders, ask them questions about the clinical part or the domain if you're in education or something else that you do not understand, so that you will be able to analyze the data even better than you would if you don't understand the domain. So we want to do the summary statistics. We have dropped the patient ID. So any identifier you have, you must drop before any statistical analysis. And so now we do a full summary of all the numeric columns that we have. We've already identified the column types and which ones are numeric. So we are using the DF analysis now. So let's say we want the DF, the numeric data. Let's change this from DF analysis to DF now to just get the numeric columns. We drop this from it and patient ID from it, and we want to get the full summary of the numeric columns. And so let's print that out so we can see the summary. So we'll say DF norm dot, and we use the describe method, and let's round it to, let's round 3. Let's round it to 3, or let's say 2. Let's mark this. Okay. So we now round this to 2 so that we don't have all those long 6 numbers. So we have the full summary of the numeric columns. If you use describe, it just takes numeric columns. It gives you the count of the age 400, so we don't have any missing value in age. So you can use this to just scan and see that systolic blood pressure has missing, blood glucose has missing, BMI has missing. This you cannot just use the mean for this. They mean something. The mean does not work because people can have different systolic blood pressure. Blood glucose, the same thing, and the BMI, the mean might work, but it's because this is clinical science. Everything has a meaning. Okay. Do you understand up until this point?
Yes.
Yes.
Okay. Hold on. Okay. So, sorry, I'm talking a lot. I have to take water in between. What we expected our outcome to be is that the systolic blood pressure mean, the mean of it should be 130.2. So we want to look at this mean. We know what it means. We know standard deviation. This is the minimum value. This is like 25th percentile. This is the median. So we'll do 25th, 27. That's what we use to first interquartile range. We use this 2 interquartile range we use this 2 to calculate interquartile range. This is the median. This is the maximum value. And so when we look at this, we see that the mean of the systolic blood pressure here, we have a mean of 130.17. We have the median to be 131. So you see that if the mean and the median are not so far apart, you can really trust the data more. Okay. So we'll look at all of this and we'll see. Let's look at previous admission. We don't have the readmission rate here. So the length of stay is there, complete. So we know that the 30-day readmission rate that is published that we're looking at is approximately 28 to 35%. And the real hospital rate that we know in real world scenario. And because when you're given this kind of data set, you have more information beyond just this data, right? And so we have the real hospital rates that range from 15 to 25% for the general wards. So we use the average mean, and we know that this mean is easily influenced by outliers. For instance, if somebody is hyperglycemic and the person has a glucose of 350, it will pull it up, everybody's blood, it will pull the mean up, and you think the mean blood glucose is high. So you know how outlier can affect the blood glucose average. And then when we see the median value, the middle value, we always like to use median because we know it's more robust to outlier. And so if we have a skewed clinical variable, let's say skewed, like maybe, let's see which one is skewed here. Length of stay will definitely be skewed because you can see 10, then you see 1. So you see it is skewed, and it might be mostly right skewed. because we can see 10, so 1, 2, 3, 4. So 10 and above are 4 values, and less than that are 3 values. So it will be mostly skewed to the right, something like that. So a right skew is expected for things like length of stay and also blood glucose when you count it like this. So you can actually look at these numbers and know exactly what it is. And then if you want to tell a story, you use visualization also. So say 1, 2, 3, 4, 5 numbers are very high, 3 numbers are low. So you know that the high ones are always on the right, so it will be right skewed, right? Because few of these people, when we look at most patients, if we look at the cluster of this, 1, 2, 3, so let's say blood glucose, all these ones are near normal. 1, 2, 3, all near normal. 1, 2, 3, 4 near normal. And then the heavily hyperglycemic is just few, 376, 195, thereabouts. So if we want to have impossible clinical values, the things like BMI less than 10, they are impossible. You know that this is a problem. And then age less than 0 is impossible, because we are looking at age between 18 and 90, right? Age between 18 and 90. And then you have systolic blood pressure that is greater than 250. You know it is impossible clinically. It won't read. So you know that those are data entry errors. So you understand what I'm trying to do here now? I'm trying to give you indicators, and sometimes if you're not in the domain, you'll be lucky enough that you have a manual that gives you all the indicators of correctness for each field. You always have something that gives you an explanation of the data you're collecting. But most of the time, as a data scientist, as a computer engineer, as a software developer, the customers do not know what they want. They just want you to perform a miracle and know what it is that they want. They don't do a good job in explaining. And so if you want to go into software engineering, you do good by focusing on a field. So if you want to focus in the field of medicine, you learn some domain, you do a lot of studies in a domain, read some statistical concepts, look at the data, sit with the data for some weeks before you even have your first inception meeting to look at this. Have questions you want to ask, sit down with cross-functional team to find out exactly what the data means, what the clinical reference ranges for the data set is. If you are not giving at the point where you ask, what are the clinical reference range? So you need to be the one asking the questions. And when you're asking the questions, you need to know before you ask. You don't know what you don't know, right, until you read about it. And so now we know that we need a reference range. How will I know what is the highest and what is high and low, what is categorized? So when you get your lab results, sometimes you see where something is marked as low, abnormal, high, abnormal, and then there's a range within which your lab result is normal. So you need those reference range to understand the meaning of the values, because in clinical science, all these numbers are not just numbers, they have meanings, and that's why you cannot just replace. Okay, so when you know that BMI cannot be less than 10 clinically, it's not even possible. Age can never be less than 0 if you're doing the age in years, because it's in years here. And you have the systolic blood pressure can never be greater than 250 here, because the machine will record up to that point. And so when you see all those things, there are data entry errors here. So when we look at systolic blood pressure, you want to make sure you don't have that. And so you can actually even code this in the script. So if you're having a script that automatically does several data in the future, you're not just going to, you can create a script. You're not going to just tailor it to this. And it's always even easier to create a script when you have a data entry standard where all of the column names are named the same thing, or there's a particular standard, maybe use fire or use DICOM if it's for images, and you know exactly how the columns are labeled. You can create your scripts to take those information from those columns, and then you can now use a script to say so instead of printing this now, when it describes this internally and it gets any of these values that are within this range, so these are all scripts you want to do something about it. Okay, so now we know that we are doing exploratory data analysis by asking questions that the data does not contain, and by trying to know things from the domain. Now, when we have a mean and a standard deviation, it will just tell us the center of the spread. But again, like I said, in clinical data, there's always complex shape of spread. So blood pressure, for instance, would cluster mid-modally in something like in cardiology, right? If you have cardiology and general, the blood pressure will cluster differently. Right? The length of stay will almost be right skewed, because people that stay longer will always be there, because most patients leave the hospital quickly. Within 72 hours, most patients go. But we have very few patients that are long admissions, right? And so you have those right skew of people that are so long. So what this tells us is that in a clinical data like this, you need to visualize your data. because visualization now will help you to see better. So you're not in the clinical field, you don't understand what this means. Visualization will help you understand and help you to be able to explain this. So you don't just do visualization to beautify your reports. You need to have an explanation of your visualization. And so let's visualize this data that we did. I'll remove all of these print statements and let us start with visualization. I want to look at the distribution, visualize distribution. So let me import. Do you all understand to this point?
Yes.
Is it getting clearer?
Yes, sure.
Yes, it is.
Okay, and let's try to import Seaborn again. Then we want to visualize our data. I've not taught you guys subplots. I think we'll do that next week. Let me not derail this. Subplots, if you already watch week 8 lesson, you see how we can use subplots. You can do side-by-side plots of something in the same plots, right? Let me just write that down as one of the things I will produce. As one of the things I will show you, so it will be easy for you to do, or I'll just give you as a reading assignment. It's not difficult, just for you to understand the numbers. So we're going to, let's say, figure axis is equal to plt dot subplot. We want 2, 3 fig size. I'll finish typing, then I'll explain to you. Let's do the figure size should be 15 by 8. You can make it smaller. You can read individually. I think as a data scientist, you should learn to research every line of code you don't understand. So it helps you to understand every line of code even better. So we'll want to create a plot, and the plot we're creating is going to compare several. We're just going to have a distribution visualization, right? And when we have this subplots method, is a method in Matplotlib, right? And it's just like, let's call it like a wrapper or a container. Let's say it's a wrapper, like when you have a container like a div tag in HTML that you use to hold other elements within it. But what this does is that it creates a figure and a grid of the subplot, and the subplots are like axis objects. You create all of this in one single cell, like we said. And if you have complex layouts, this will make it more readable. So when we have this like this first one is a number of rows, and this second one is a number of columns. So this like this will return a figure object at the end of the day. So subplot always returns a figure. If you put your cursor there, you can see more definition here, like n rows, n calls, and then other optional things. So sometimes what I do is I just try to have that, and you see the documentations and the meaning here of anything that you import. So that's why it's good when you write your scripts and you have a module, you have it well with type hints and everything, especially when you're going to use this for an API or create a script output from an API. Okay, so it returns the figure object. If you want to have a 2x2 grid, for instance, your subplot will have 2 row and 2 column like this. So what we're going to have is a 2x3 grid here. Okay, so I will do a different lesson to explain subplots, but I just want you to understand why 2, 3 here, and sometimes you see 2, 2, sometimes you see 1, 2, 2. Sometimes you have something like, let me just write this here, subplots, and you have something like 1, 2, 2. So you're having like 3 numbers. So what it means is you're plotting 2 in a 1 row 2 column grid. Okay, you're plotting 2 in a 1 row 2 column grid. That's what it means. Do you understand what I'm trying to say? I don't think I'm explaining it well. You all understand?
The last part I couldn't get it.
Okay, so what I'm saying here is that this is the number of what you are plotting, right? So you're plotting 2 distribution in a grid that is 1 row 2 columns. No, here we say this is number of rows and number of columns, right? So here is number of rows, number of columns, and then let me put PLT so you can show the definition. PLT dot. So here we have, so this is number of rows, number of columns, and then we have, this is share X, bool, all non-row, and different kind of.
Sorry, ma, is it to add additional information? Is that why we use the subplot?
No. You want to put your side-by-side plots to be able to compare. So it's like you want to compare 2 things at the same time. So you don't want to have just one plot histogram, you want to another plot histogram, and then you'll be switching pages to look at both. You want both of them to be. So if you have watched week 8 lesson, you would have seen that I did a subplot there that compares 2 things. That compares when we have when we want to illustrate the central tendency, where we say even if a data is right skewed, it begins to go towards a normal distribution as the data increases. So when you do data analysis, most of the time we always assume normality, and it's because of the central limit theorem that we assume normality that states that. So when you look at week 6 lesson, so I'm doing this with the assumption that week 8, with the assumption that you've watched week 8 lesson. So by the time I send this lesson video and you rewatch it, a lot of things will make more sense when you have watched the individual lesson comprehensively from week 1 to 8. All right. So now we want to plot to a subplot, and we want to have the clinical variable distribution. We can set the font size, we can set the boldness. Let me do this in completeness so that you can use this as a summary video for the final exam. So let's say we want a subplot title, a subtitle. Now you see that there's a lot of little things that even in colleges, even in a master's degree, and so there are things that at that level of education you're expected to know. And if you don't know, they're expected to research. And so while some things can be listed as research topics for you to do, some things will be taught to you. And so there is hardly a school that will actually spoon feed you on everything that you need to know. Some will not even tell you what you need to know. It's during your studies that you realize that I don't know this. And so that's why the School of Programming exists, so that we'll tell you what you need to know before something, and we'll have a structured pattern that now allows people to learn better than they've always learned. Because when I was trying to learn software, there was no single resource. I did a lot of online resources, massive open learning. I started from EDX, whatever. I did a lot of stuff, and as much as I did this stuff, I was not able to tie it together. So everything was theoretical. You go for lectures and you see that it is still theoretical. So how understanding how to do this? And it's theoretical. And then I got to college, I realized that even the professors know it on theoretical level. They don't really know how to write these codes. And so they teach you the theory and then you are lost. They understand the theory very well. They do it so well. But then the practical, you won't find any of them who has published a software to their name. And then I, with my curiosity, decided that I'm going to learn it, and one day I will learn it. So it took me several years to learn by myself. I'll be bouncing around trying to understand one thing or the other. And then at the end of the day, I put all my struggles into a curriculum. This is what I knew before this. And then I had this dream that I was going to teach people, because after this generation passes away, the next generation will have it tough. There will be no institutional memory. Now, because of AI, it makes it worse. Who is going to train the next AI? When the world advances, who can write raw hard code to create new innovations? Innovations are going to die in the next generation. Why? The schools are not teaching it anymore. People are looking for the easy way. Children cannot even write a letter. They just go to AI and the thing types it. They just give it a script, it types it for them, they submit. Sometimes you know that it's AI because if the person understood what they were doing, when they read this, they will know a particular line when the AI made error. AI can be up to 80% correct. I like AI as a productivity tool, but not to replace your knowledge. So who builds that AI? Somebody has to maintain, build, retrain. Somebody has to look at the logs and see that people put thumbs up or thumb down when the stuff is correct. Somebody has to go and see the responses that are marked correct and put it as a choice response. People have to be there. They are knowledgeable in the field to continue to train. New innovations come, who trains it? And so that is what we are doing now. The world has not caught up with where School of Programming is. And so I have the confidence that what you are learning right now, even if you don't see how it's useful for you today, at the time when it becomes useful, it will be a rare skill. And so when the world finishes bouncing around with all of the advent of AI and everybody hyping themselves and saying, I use AI to do this, and they begin to see the reality of the real AI and see that they don't really know what they're doing, at that time, they'll come back to the drawing board, and then we are there with it. Okay? So we have the clinical variables. So clinical variables we want to use for this distribution visualization. Let's use the systolic BP, the blood glucose, the BMI, the length of stay. Let's use the number of medications on discharge and the comorbidity score. Can somebody tell me why I chose this particular columns?
Please mention the columns again.
I'm using the systolic blood pressure. I will use the blood glucose. Let me code this. I'm going to use the blood glucose. I'll use the BMI. I will use the length of stay, the number of medications, and the comorbidity score.
As those are the columns our analysis depends on, like we are trying to work around those columns.
Yes, and something
because it has missing values. And
no, not missing value. The first one you said is partially correct, but why did we choose that? We have categorical variables that we need also for our analysis, like insurance type, discharge type, follow-up attended, and then we also have word and gender, and all of this we need them too. We also have
Okay.
age that is there too. So
Is it as a result of maybe what they consider like the diseases they measure, something like that?
okay, so let me tell you, if you look carefully at all of this, one thing they all have in common is that they're all numeric values, right? That's one thing we have. The only ones that have missing blood glucose, systolic, BMI. So you have blood glucose, systolic, and BMI. They have missing values. Now, we chose these ones for the distribution because we are thinking about the 5 research questions that we asked. And the 5 questions that I asked initially is that we want to know if what the clinical factors that are most associated with 30-day readmission, what the clinical factors are. We want to know if the patients that miss follow-up have higher readmission rates. Okay, let me see. I want to know if they have higher readmission rates. We want to know if the length of stay is different between the wards, but we don't have that here yet. We want to know if the readmission rate is associated with insurance type or the method of discharge. Now we don't have those ones because they're all categorical variable. Yes, no, male, female, different types of departments, so they're categorical. And then we want to see if there are any significant difference in clinical measurements between readmitted and non-readmitted patients. Now, what we are doing now is we are doing distribution visualization. And in all our research questions, what involves distribution analysis the most is the difference in the clinical measurements between readmitted and non-readmitted patients. So all of these are clinical measurements. All the rest are not clinical measurements. Age is not a clinical measurement. So that is why it is a numeric value, but it is not there. But length of stay, these are all clinical measurements. So why we chose all of this is because when we come here, we see that we are taking all of the clinical measurements, which is supposed to be the core thing that everything depends on. Okay, the clinical measurements, that is the thing that we depend on the most, that we need to have for us to be able to have meaningful analysis. The clinical measurements are there. They want to see now what of these measurements strongly correlates with the questions that we're asking. Now, do you understand? So I thought you'll see by me writing clinical VAS as the variable name and say why I'm selecting this. Why? Because they're all the numeric and they're all clinical measurements. Now, do you understand now?
Yes.
Now we want to let's just plot it first and I'll explain. So let me do it as a loop for AX. Let me do for AX call in. Let's zip the clinical variables. So I'll flatten it, axis.flat. These are things you need to actually read and research. So I'm going to teach you guys how to research. We'll leave things like this and you have to go further to look at. So what does it mean when I do a subplot in Matplotlib? What does it mean if I do plat? What are the methods? So know that this is not a dedicated course for Matplotlib and so, but we touch on it. And so your job is to go further and read about Matplotlib. It won't take you more than 2 days to read about this, even a day if you already understand Python. Okay. So we want to use SNS because we imported Seaborn as SNS. I hope I did that. So I'll say SNS dot. I want to do a his plot and I want to drop all of the columns that are not available because right now for the clinical data that I have, the significance is too costly for me to replace by the mean or the median. Okay, so I'll say df call. So before I go further, can I go for 1 more hour? Are you guys available for 1 more hour or you want us to break it at some point? Can you guys hear me?
Yes, I'm available.
Okay, so we'll do a his plot and for this we want to drop any. So you can see what we learned in the first 4 weeks. We're using them here. So we get the column because here what we did is for AX call. So that call now is like we're looping. We'll drop all of the missing values and then let's put KD equal to true. I want you to reset this. I think I should have mentioned it in one of my live video. And then we put AX equal to AX. Research all of these meanings and let's have a color for it. Let's put the color to be, let me say steel blue, and let's put the number of beans here. Research every single of these attributes. Let's put a title here. Let's say ax.set title and the title we want, let's put the title as call. So the title is just going to be the name of the column. Okay, so when it loops any column it gets to, let the title be the name of the column so we can understand it. And then let's have a line a line that shows us distribution. I'm just thinking of. So let's have a line for the mean, a line for the median. So let's do like ax dot axv line. So all of these are different methods and attributes that you can research for Seaborn and Matplotlib, and you have to research them in details. We can't touch every little detail of all of this. If not, it becomes a course on its own. Right? GF call. I think I'll put this in square brackets. So we're getting the mean of this. So I'll put dot mean. I think I won't go too far so that I will actually confirm if this works well first. I'm just trying to, let's put the line style. Line style, is it written with just line style? Let's see. If it's wrong, it's okay, it's correct. And let's make the line style dashes. I think it's 3 dashes. I should have made one mistake in the lesson video and corrected that. So it should be 2 dashes. I think I put 3 in the lesson video, it rejected it. And then we saw that error. And then we have the label, and the label we want is to say this is the line of the mean. Now you need to understand this very well when we start machine learning course, because the next course sequel to this is machine learning and for the artificial intelligence part. And if you don't understand this, you get thrown off in machine learning because you must do all of this before you actually even start the machine learning. So ax.axv line, we want the median also, right? That's what we said. So I'll put df call and dot median, and then I will have the color is equal to green, the line style. Let's put a single dash. I hope this works. I'll put the label here to be median. So there's Copilot, which is a tool you can use to autocomplete. Again, it's not always correct because AI is still learning. Some people use it to just get a hint of what they're doing. So when I say AI, mostly is a productivity tool more than it is a replacement tool. The world will catch up and know that soon enough. So just try not to be common, and AI cannot replace you. So let's make a tight layout, and then we will show. All right. Should we print? No, let's just show this. I wanted to print a story to explain it. Oh no, clinical vars. Where did I put it? Name error, clinical var. Where are you? Clinical vars here.
You have var S. Okay.
Yeah, I did that. Okay, so we have non-medication, the column, non-medication, number of medication, is it S? So you see just the spelling, non-medications, yes, so it's S. So I put non-medication here, all right. So clear again, and then run. And then we see, this is what the subplot is. Can you see the screen?
Yes.
Sorry, let me reshare because I think I shared only one cell, and so you won't see the plot, okay? So now, can you see it now?
Yes, now I can see.
So you see a subplot just gives you something you can compare everything at once. So when we use subplots, we use it for this kind of distribution visualization. So you can see the different clinical variable distribution. So you see how it came out nice. So we have the line, the first AV line that we AXV line we created, that is red in color, just shows the line of the mean, and the green one shows the line of the median. So we just made it a single straight line for median, so we'll know, and the mean dotted line like that. So we can see the mean and median for the systolic blood pressure. So when you look at it, you'll see how this is. This shape is approximately bell shaped. When you look at the shape, bell shape just means that it has a normal distribution, and so we can use this for parametric tests. This is okay, it's normal. Now this is almost left skewed when we look at right skewed, when we look at this blood glucose, so it's slightly right skewed. So, and you will see that most values, when you see the right is more plenty here, and we'll see that most values are near 100 to 120, whereas that's where the median is, right? 100 to 120 here, they are near there, and the long tail is towards 250 here, where the long tail is. That's what you know whether it's right skewed or left skewed. So you see where the long tail is. And then we have the BMI is near normal also. It's almost bell curved when we look at the curve. And the skew to the right is a little slight. You can see it's not perfectly in the middle. It might be in the middle here, but it's just slightly skewed. Once it's slightly skewed, you can leave it. And then we'll see the weights clustered around 25 and 30 BMI. Look at the two numbers here, between 25 and 30. So you can see here 100 and 120 here, 120 and 140. And then we look at length of stay. This one is right skewed. You can see from 2.520, you can see the length of stay is right skewed. And I mean, here is normal distribution, but it's Normally in real life it's always right skewed, right? But this is almost normal. We can see we don't have the bell curve. At the same time, we don't have anything that is skewed in one place. We can see how it is. So we can just see the length of stay. We have between 1 and 20, we just by the design that we have. But you have to be aware that when you get real hospital data, you hardly have it normal. Okay, you always have it to be strongly right skewed in real world scenario. And then the number of medications that we're giving at discharge is roughly uniform. When they discharge, we can see that it's roughly uniform. It's still random integers between 1 and 15, and the comorbidity score is near symmetric. So we can see it's almost a straight line that we have here. Near symmetric. Look at where the median is, look at where the mean is. Everything falls between 2 and 3, and so we have like a Poisson-like distribution. So when you look at the different distribution analysis, that's what you see. So anytime you have a normal or a symmetric distribution, you have can do a parametric test. And the parametric test we have t-test, Pearson, R, ANOVA, and all that. I don't think we did that in week 8, but I think it will be in week 9. And then when we have a right skew data, we want to consider using log transformation or parametric alternative, like when you use t-test and Spearman instead of Pearson correlation. And then when you have a uniform, like flat, the values are likely across, the values are equally likely across all the range. And so you might just indicate that you have a categorical variable that is coded as continuous, but this is not a categorical. It's actually a categorical variable, but it's coded as continuous because it's always between 1 and 5. Other belong to 1, 2, 3, 4, 5. All right. So the categorical variables we have are gender, ward, discharge type, follow-up attended, and the insurance type. And we want to have our outcome variable, which is readmitted 30 days. That's the outcome variable we have. So before we do any group comparison, we need to know how many patients fall into each of the categories. So we don't want to have imbalanced category where we have only 10% that are uninsured. It will limit how confident we'll be at the end of the day to draw conclusions about that group. Okay, so now I'm going to close this one and I'll go back to what we were doing. All right, so we want to do the categorical analysis, and for the categorical analysis we want to have the categorical variables. I'm just going to comment this out so that we don't have to do it again. Do you guys understand, or you need more explanation?
I'm getting it.
Okay. By the time you rewatch it might make a little more sense. By the time you watch the individual videos and watch this. So the biggest issue with all of this is knowing how to tie up everything you've learned over the weeks together and know when to use them. But the more you practice, I can give you more simulated data and questions to see. And if you have gone through your final project stuff, you'll be able to use this now to your final project even easier. Okay. Let me see, do I have the readmitted 30 days? So the outcome variable is the probability we have here. Readmitted 30 days is mp.where. We'll just put random, yes or no. So let's have readmitted 30 days. Now these are the categorical variables we have, the ones that either male or female, yes or no, the type of discharge, the type of ward, and all of that. So we'll say for call in advance is equal to TF call dot value count. Then we have ACTs is equal to DF call dot value count normalize equal to true is the 100. I don't think this is correct, but let's try it first. Let's round this to 1 decimal place. And then we'll have the summary. We'll do this in a bar chart. Let's do the bar chart of readmission by word. I'm thinking of what is going to make more sense here. Okay, I'll do this and then I'll explain it. Let me just do it and see if it's correct first, then I'll give an explanation. So let's have a data frame here. Now count will be equal to, let's say count will be equal to the count that we have here, value count. So we have percent. Let's make percent equal to the percentage. Will that work? So we use count percent. Let's print. Why is this wrong? I need to make it a dictionary. I think I used a wrong raise here. Yes, that's the problem. And then I want to print. Let's print the column. Let me use a format string. I will start on a new line, and then I will have, let's use a column raise this, and then something like this. Then we'll print the summary just to make it formatted nicely. And then I want to have the bar chart, right? So let's say readmit. Let's say readmit by word. That's what we want to do. So bar chart will be, so now we're going to use the aggregation that we learned in the earlier lessons where we use the group by. So we'll say df dot group by, and we are grouping by the word. Do you all understand?
Yes.
Yeah. So most of all of these attributes and methods are things that you can research to see if I'm working with lists, what are the different list methods that exist, okay? So it's not something that is in the context of data science, but in Python as a whole. And so we have group by word, and we want to have readmission by word. So we want to group by word, and what we want to get that we're grouping by word is the readmitted 30 days, right? 30 days. And then that's apply, I think. So now we want to apply. Let's use lambda, lambda x. So we want to get all the yes if they are readmitted after 30 days. So say x equal to yes, and then we want to get the mean of that, and we want to multiply it by 100, put it in percentage, and then we want to sort this, but we want to sort it before we plot. So we'll sort values, and we want it from, let's say ascending is equal to false. Okay, so now let's plot. So we'll say readmit by word dot plot. We want to have the kind will be equal to, we want to have a bar chart. We want to have the color. Let's say use steel blue. I find it to be very cool and okay to use. And we'll have edge color. Let's make the edge color white. And then let's put the title, and let's say the title is 30-day readmission rate by word. And we want to even put that this is in percentage, right? And then we want to apply PLT. Before that, let's put the labels. That's y label, and we want it the y label. The y-axis now is going to be the readmission rate, and the x is just going to be the labels of the different groups, like the words. So let's say readmission rate. You always have to put the unit. Your plot must be able to tell a story, and we want to, because we are going to put the group, the word names, let's rotate it so we can see it. So you do PLT, we rotate it with X ticks like this, and we'll write rotation. You just put a degree of an angle you want to rotate, let's say 30 degree. We don't want it to be perfect rotation, and let's make a tight plot. So let's say tight, and then we show. Okay, let's run this and see. Okay, it's working fine. You can see this well. Can you all see it well?
Yes.
So we can see 30-day readmission rate by word.
Yes.
Okay. So we can see the different word. We don't see a major difference between the different words, the readmission rate. Okay. And we didn't do this we can actually do this by gender. Did we add gender to this? Let's go back there. I want to see something that will make more sense. So we have gender, we have word discharge type. Okay, we didn't use gender. We didn't use the gender here, except if we did and we didn't plot it as differently as we would have wanted. So when you do plot, sometimes when you do a plot, you have to go back to it and see if what you have plotted is something that you like to see. If it tells a story enough, or you want to just change a plot, or you want to do a different kind of grouping. All right. So what we did here, gender is not part of it, but we can do a gender distribution where we have the gender of the people are male, or group them by male, female. But here what we did is we just group by word only. Then you can group by both word and the gender. So you have it stacked with different colors. And something I wanted to go and practice and do yourself. Okay. So we readmit by word. We can change all of this one by one to do by gender, to do by discharge type. So when we look at by word, we are seeing that everything is almost like they're not so far apart. The readmission rate is not so far apart. So now that we have that, we want to some kind of questions. Things like, do we want to compute the readmission rate for self-discharge versus home discharge? If you ask questions like that and you see that do you have self-discharge patients having higher readmission rates than home discharge patients, you're going to use that. So when we look at this, we'll say that this doesn't really tell a serious story to see that the readmission rate is worse in a particular ward. But we can see oncology has lower readmission rate. Why is it lower? Do they have longer hospital stay? You'll see general has higher readmission rate. Today they discharge faster. Orthopedic and general are not so far apart, and you want to ask those questions. Now you are looking at this plot, and does this tell a story? What story are you going to write? Because the story is something that you will write, and you can produce a script that writes that. So how do we answer some of these questions? We use a correlation analysis, and that's where we come into correlation matrix. In correlation matrix, I was hoping that we would have gotten to the point where we do week 8 content, but I want us to follow through. I don't think we are so far from week 8, but what we did in week 8 was, week 8's topic was mostly probability and statistics, right? And we have looked at, okay, we'll soon get there. Let's just do this and finish this data analysis so that you will know how to analyze your data. I want us to just not take more time than we have taken, and I will do that here. So we have this, and we want to do correlation analysis. So we want to encode everything as binary for correlation, where we have the readmitted 30 days, we have them yes or no. So let's turn it to binary. And if you want to turn it into binary, you use as type, and then you put as type int like this. Okay. So let's say we have df binary is equal to, let's say df readmitted 30 days. We want the ones that are remitted in 30 days to be yes. So we'll take only those ones, and then we'll do dot as type int. So we convert this as binary for correlation. Then we want to select the numeric features, and when we select that, we'll still drop the patient ID. I think we did that at some point where we selected just the numeric, yeah, or clinical value. I'll just copy this to make it easier, but I will add the ones that are missing. So here I'm going to do numeric columns. So this is how you write reports. If you are a data analyst and you're supposed to be writing a report, you will do all of that, save your different charts, put explanation, do different charts that explains and tells a coherent story, all right? That can even prove without a doubt that everything is as it's supposed to be. So let's say these are the numeric columns. We want age to be part of it. No. So we'll do age, we have length of stay, we have, we don't have number of previous admissions, let's add it. So that has previous admissions, and then we have number of medication, we have comorbidity score, we have systolic blood pressure, then the blood glucose, we have that, yep, we have blood glucose, and then the BMI and the, so let's put this readmitted binary, which is a new column that we created. So you see how we re-engineered something, right? We added a column that doesn't exist.
Yes.
So we take all of this and we don't put the patient ID. Now I want to have the correlation. So this is where we started week 7, that we had not looked at in a live class, but we did that in the videos. So let's see what we do with correlation. So when you want to use correlation, there is a core method that we use. Let me use it as core like this is equal to df, we'll get the numeric columns dot core, and then we want to have the heat map, because when we do correlation analysis of the categorical variables, we most of the time, in fact, heat map is what we always see most of the time, and I've showed you how to interpret heat map in week 6, but we'll look at that again. So figure size, let's say fig size is equal to, let's make a smaller figure, let me do 10.7, and then I want to have I'll use SEBON for its SNS.heatmap, and I will get these correlation values, and then I will plot it. So I'll say the heat map will be the core, let me annotate it, so I'll say annotate equal to true, and then I will say let's format this is equal to 0.2f, and then we have let's put the column up is equal to, let 0 be the center, let's do the vmin will now be -1, and then the vmax should be 1, and then we have the line width, let's make it 0.5. Let's create a title. So you see how we use matplotlib and SEBON together. So we'll have clinical matrix, patient outcomes, data set. Now let's just show, let's make the layout tight. So plt.tight layout and plt.show. So we want to see, the question we're answering is what correlates most with readmission, and we want to have the let's see whether we can even print something here. Let me print, let's say correlation with readmission, just formatting it to be neat. And so when you do data analysis, you need to make sure you're having very clean, well labeled, well annotated plots. because that counts a lot for good plots. So we want to have bad binary plus job, readmitted binary. Right. So let's see if this works. Oh no, it doesn't work. So readmitted 30 days. I didn't spell it correctly. 27 readmitted 30 days. So data frame object is not callable on 89. So I did correlation is equal to df. Sorry, I'm supposed to put this in a square bracket. I'll clear and I'll run. I still have color map is not known. Sorry, it's not color map, it's CMap at the right. So I put CMap here. From what? Color map name is not known. Oh, here's the value that I put there for the CMap. So I use RD1. Now we have that. So when we do correlation analysis, we know that, can you all see the screen properly?
Yes.
So when we do correlation analysis, we know that everything correlates with itself with perfect 1, right? 1. And when you look at this, when things are correlated, we look at the color matrix we use so that we'll see whether they are partially correlated, very correlated, no correlation, and that. So I think we did that in week 7, where we look at the different correlation matrix and exactly what they mean. So when you have a heat map like this, you have all of the different categorical variables or all of the different variables you want to compare. And when you compare them, we want to see the values between, so let's say we're looking at age and comorbidity score. It is minus 0.02. So you're looking for the things that look more green, and you want to see they are slightly positive correlate. So as it goes towards this one is positively correlated, and as it goes down towards red, it is negatively correlated, and when it's like closer to 0, there is no correlation. Okay, so you all understand how heat map shows the relationship. So anything near 1 strong positive, near -1 strong negative, and near 0 is a weak relation. So when we look at this, what and what correlates? Now, what and what correlates? You can now write your report and say, let's look at the comorbidity score here. Comorbidity score, we look here and see we have this with the readmitted binary. So this, we did not rotate this. Maybe we'll do this thing to rotate so we can see the columns that we have here. All right. So we have there that we are correlating with the readmitted binary, and we look at comorbidity score. It's almost green. So we have this score of positive 0.22, which is, if we look at it, it's the darker green than any other one there. So when we look at the other side too, it's the same thing, readmitted and comorbidity score. And we have this, and so we have the strongest one. As the strongest positive correlation is going towards green, right? So it's the strongest positive correlation, comorbidity score, with the readmitted. Now look at number of previous admissions. That's the next one with readmitted binary. It's a little green, but it's 0.07. It's with this data we have, it can predict, but not as much. So it has a weak positive correlation, right? So you can see how the color code will help you. So any color line is like this, is just almost not really significant, right? And then we'll have a number of medications. Now take note that we're using random data. Every time we refresh, it regenerates randomly. So your numbers will not be the same when you interpret, but in the clinical one, we have fixed data, real data, that you either be loading from an API or you're loading from a database, and then you pass through a cleaning method and comes here. So your data will always be reproduced exactly the same. When we see data, we can actually make sure we want to reproduce the same thing if we want, by putting just a particular variable. But here we have the age. Let's see where age is. So these are the questions to answer. So when we look at systolic BP2, we look at the negative, it really does not have any correlation as much. So you look at each of them. So you can do age and readmitted binary, right? And look at it. So sorry, this is readmitted binary. I want to say age and readmitted binary. Okay, this is the value. Sorry, it's not 1, it's this. So we say age and readmitted binary is not correlated as much. It has a negative correlation, or not as much. It's just slightly below 1. Okay, this is readmitted binary and readmitted binary. I was making a mistake. And then when you look at age and other factors, so you can take age and see if age, what factors does this age affect. So you look at BMI, it's just weakly positively correlated. So age doesn't really affect anything when we look at it like this. So you want it to be significant, have a point like 0.2, minus 0.2 to see that there's something negative going, weak negative, and here we say weak positive going up. And then we come and look at readmitted, and we look at it with other things, and we begin to see that readmitted is having a positive correlation with comorbidity score. Then we'll look at number of previous admissions. Where is it getting high a little? It's just a little on the number of previous admission, the systolic blood pressure. So you saw people that are hypertensive slightly affects that they are more admitted. Then we now look at the systolic BP and see where it is more correlated. It's just previous admissions little. Why is that the thing? Because you most likely have systolic BP measured for people that have been admitted before more than the ones that have not been admitted before. Then you have blood glucose, and you want to look at where the correlation is strongest, and it doesn't really correlate as much, but you see 0.07 going towards positive, so it just has weak with everything. Then BMI too, interpreted the same thing. It does not have any correlation with anything. We look at length of stay. There is no correlation worthy of mention. We look at number of medication that are on discharge. It really has no correlation. And then we come here to look at the comorbidity score, and we can talk about it has a correlation with the readmitted number of readmitted 30 days. So you can see that. So the only thing that is worthy of comparison here now is which of these categorical variables, which of these correlates either positive or negatively with those are readmitted within 30 days of discharge, and it's the comorbidity score that we can see here. So it answers the question. Okay, so the patients with higher comorbidity score are moderately more likely to be readmitted. That's one of the points you write as your conclusion there. And then you will know that there is really no linear relationship between the rest as much. Okay, so I don't know if you understand how I interpreted the heat map.
Not fully, but yes, I'm trying to get it. Yeah.
Okay, so we'll see the correlation here. We printed it here to see. And when we look at comorbidity score, it's the highest because we did it in descending order, right? And the comorbidity score is the highest for readmitted. So if you don't want to do a plot, you can just use this to write a report and see that patients with higher comorbidity score are more likely to be readmitted within 30 days of admission. Now, we said it several times that correlation is not equal to causation. That something is correlated is not the cause. The comorbidity of a person is not the cause of the person's admission. So it correlates strongly with readmission, but patients that definitely has multiple. When you say comorbidity score, is that they have multiple chronic diseases. And when you see people with multiple chronic diseases, they tend to be older generally, right? They tend to be older. They tend to be people that will be on more medication, and they are more likely to even self-discharge because they're just tired of life already. So when we do this correlation now, you just have, so with real data, what you get will be more complex. So you have complex interacting factors. And so it's not going to be a simple cause and effects that we just saw there, because we simulated the data, we had control over what we wanted to see, right? But so when we have in clinical research, it's going to be we're going to be doing a lot of multivariate regression, and we'll be doing a lot of score matching. We're doing a lot of randomized control trials, not just exploratory data analysis. So I'm just putting it out there and letting you know that in the real sense of clinical, it's deeper than what we just see. But we're using this to just learn exploratory data analysis. All right. So clinical exploratory data analysis here, it's useful clinically, and this is where the use really is, where we group our outcome variable and we compare each of those profiles, right? So when we get to week 9, when we look at the different hypotheses that we generate a hypothesis, we begin to look at the different score that we have. So we can do more group comparisons here that will give us even more insight into the data, and then we'll begin to form hypotheses. Do you all understand?
Yes.
Okay, so with what I've done now, we've covered most of what we want to cover. We didn't cover week 8 probability fundamental yet, so maybe next week we'll do week 8 and 9 together because it's very short and it will help us to understand this. We'll first of all look at group analysis when we come back next week, and then we'll move on to form the hypothesis with the group analysis, and then we'll do the probability and statistics, and then get to week 9 content that is going to be, I'll try to put week 9 available early so that you can read you can study week 9 before the class, because it seems like week 8 lesson has not been well studied yet. And so if you don't see how we do some basic stuff like week 7 lesson, try to understand week 8 also. And then when you come back, if you're able to do week 9 before Saturday next week in videos, you try to do that so that we'll see exactly how we do hypothesis testing and how we either accept or reject an hypothesis. And when we do that, I will even see if I try to use a different data set to record week 9 lessons that goes from beginning to end. So you can have one summary video apart from this live class, and then we'll follow through next week to get the rest of the content into next week live class, which might be the last live class for this course, and try to see if we can even include week 10 here. And whenever you get your week 10 lessons, you just go back to watch this video to know exactly what it is. All right. Do you have any question before we go?
I think for now.
Okay.
Now, go through.
All right. So thank you all of you, and I will see you next week.
Thank you.
Thank you.